SPH4U wave nature of light. 5.2 wave interference. So wave interference, it can be described in two different ways, constructive and destructive. So constructive interference is when waves add up together and they produce a resultant wave of a higher amplitude. So you have this wave plus this wave, that would equal a wave like this with a higher amplitude. Destructive interference is when waves diminish each other and produce a resultant wave of lower amplitude. So you have this wave plus this wave, so that is equal to a wave of a lower amplitude. So this is a diagram of something called two-source interference. So there's two sources which are emitting waves, and the blue, those are called nodal lines. So those are lines where there's destructive interference. And then there's the lines in red, which are called lines of constructive interference or antinodal lines. And the nodes are points of zero amplitude, while the antinodes are points of maximum amplitude. And this line, which is called m is equal to 0, that is called the central maximum, because that's the central antinodal line, and antinodal lines have constructive interference, so it's a maximum. So there are some equations for the wavelength of the waves that we can obtain via the nodal and antinodal lines. So for any point P on the nth nodal line, there is this equation. So the absolute value of the distance from the point to source 1 minus the distance from the point to source 2, that's equal to n, so that's the nodal number, minus 1/2 times the wavelength. So this is source 1, this is source 2, there's this distance d between them. So this is the central maximum. So this is when m is equal to 0. So this is n is equal to 1. So this is the first nodal line. And this is also n is equal to 1. This is m is equal to 1. So that's the first antinodal line. And likewise on this side. Then this is n is equal to 2. N is equal to 2. This is m is equal to 2. M is equal to 2. So n is equal to 3. N is equal to 3. So this is for nodal lines. For antinodal lines, there's a similar equation. So absolute value of P(S1) minus P(S2) is equal to m. So that's the antinodal number times the wavelength. So let's just say that we have point here, and this is on a nodal line. So P(S1) would be this distance, while P(S2) would be this distance. So we'll go over an example of this on the next slide. So two identical point sources are 5 centimeters apart. If the frequency of the wave is 8 Hz and the point on the first nodal line is 10 centimeters from the first source and 11 centimeters from the second source, what is the wavelength and what is the speed of the wave? Alright, so it's on the nodal line, so we use this equation. Ps2 minus Ps1 is equal to n minus 1/2 times lambda. So we know that Ps1 is equal to 10, Ps2 is equal to 11, and n is equal to 1. So we get 11 minus 10 is equal to 1 minus 1/2 times lambda. So 1 is equal to 1/2 lambda. So 1 divided by 1/2 is equal to lambda. So 2 centimeters is equal to lambda. So that's equal to 0.02 meters. And then now what's the speed of the wave? So recall we have this equation, v is equal to f times theta. F is 8 hertz. So v is equal to 8 times 0.02. So that comes out to be 0.16 meters per second.